In section 4.3, they go through a brief discussion, and they don't present any problems in Sapling on this, but it talks about where is the function increasing and decreasing. And the main definition they give that sets you up for section 4.4, something we're going to be doing in a second, is where the first derivative is greater than 0, where the slope is positive, it's increasing, and where this first derivative is less than 0, where that is where the slope is negative, is where it's decreasing. So it's increasing where the slope is positive and decreasing where the slope is negative. That's something they bring up in 4.3. And so I tell you what, one question that could be asked, let's go back to this problem that we just did in Sapling, okay? I want to do this. Those of you that were just with me, here I've got this on my screen that I want to go to my iPad. And if you were given the situation, and you're going to be asked this several different ways at several different times, where is this function increasing and where is it decreasing? Okay? So you can see here's the given function. It's a cubic function. Where is it increasing and where is it decreasing? All right, what we're going to be working with is the fact that the situation is that, what does that graph look like? Okay, it's a cubic function, right? And so on a graph, it's going to look like this, right? So what you're going to be discovering and finding and doing a problem like this is that, and this is they talk about, if you were asked, where is this function increasing and where is it decreasing, then you'd recognize, if you had the graph, you could tell it's increasing here from here to here, and it's increasing also from here to here, right? And it's decreasing in between. That's what you're going to do to answer the questions. And notice we took the derivative and found the critical numbers to be 1 and 3. So the 1 and 3 on the number line, they must be in the order of this must be 1 and this must be 3. It's where the slope is equal to 0, right? So that's 1 and 3, and therefore the function is increasing on this interval, which is, so I'm going to say increasing on negative infinity to 1. And it doesn't include 1 because at 1 it's not increasing or decreasing, but it's also increasing over here from the far side. So that's 3 to infinity. All right? So that's increasing intervals, and decreasing is going to be in between. Decreasing interval is from 1 to 3, and it doesn't include the endpoints. Okay? So 4.3, that's basically what they were talking about, is determine where is a function increasing and decreasing. And we're going to do more with that in 4.4 right now. Okay? So any questions on what I just did? Okay, let's go back to the slideshow. And I'm going to trust that these slides are wonderfully, I've looked through them, but this one is, that last one threw me just for a little bit on that 4.2. We had an incorrect statement there. So here we go. Chapter 4, this is section 4.4 now. And notice what we've got. We've got 2 tests. They're called the first derivative test and the second derivative test. The first derivative test to find local extrema is saying, where are relative max and mins? So use the first derivative test to find the max and the min, and use a second derivative test to find the max and min. That's what these tests that are coming. I'm going to ask you in a little while on a quiz and on a test to do at least one of those. On the quiz, probably both. A first derivative test and a second derivative test. So you're going to need to know this. Also determine the concavity of a function. Where is it concave up? Where is it concave down? Okay, we'll talk about that. And inflection points. We'll discuss this in just a minute. Okay, so this is section 4.4. Let's go to this, the first derivative test. Any questions up to that point? Okay, I think you're going to have to unmute yourself if you want to say something, because I believe you are unmuted, but you all have your mics muted. So All right, pay attention here. So the first derivative test, it's saying, let f be the function continuous on an interval. Suppose c is a critical number, all right? Then the idea is if the derivative is greater than 0 for any portion of that interval, if the derivative is greater than 0, if it's positive for any portion of that interval, all right, then the c that you get, if everything's less than that and it's going up to it, if it's greater than 0, so the derivative is greater than 0, so it's going up, then c must be happening at its max. And then notice that if the slope to the left is positive and the slope to the right is negative, it's less than 0 to the other side, that means it's got to be at a peak in between. So that diagram you drew before from what I had written, it had, from the left-hand side, it was going up. And then on the right-hand side of the peak, it was going down. So that means you got a local max. That defines it, it's a local max. The first derivative test is saying the slope was positive to the right, left, the slope is negative to the right, therefore we've got a max in between. And for the second part, it was going down when we approached 3, from the left-hand side. So it was going down on the left, and then it was going up on the right. Therefore, down on the left, up on the right means it's got to be at a bottom. It's got to be at a minimum in between. Okay? So that's indicating that the general rule of thumb of what the derivative test, first derivative test is showing. And notice it says, if the derivative has the same sign on both sides, then it's neither a local max or a local min. And that happens several different times, okay? So we'll show that also in just a minute. Questions on that at all? We're going to do a couple of examples right now. Okay, let's go to this. Okay, so I want to go to, this one's a little more complicated. I want to go to this situation right here, okay? So look at this. We've got information from the graph of the derivative. No, I tell you what, that's not what I want to do. Let's go on. Okay, so rectilinear motion, that's something we're not talking about right now either. All right, so but let's go to concavity. I'll talk about that other problem in just a minute. I'll tell you what, let's go and do another problem I'm going to do another problem on my iPad together with you right now. We'll do it from the start to the finish, and we'll do that. So right now, I'm going to get out of this and go back to my iPad, okay? So we're going to do a new share and go to my iPad. Okay, so let's do a problem. One that I've got here is, let's look at this one. Let's look at f of x is equal to 2x to the third minus 9x squared plus 12x minus 5. Okay? And there's the function that we've got, and we're going to work with that situation. You guys hang on 1 second. I'm going to take a break just for a second. I need to change something on our screen so the class, this meeting will last a little bit longer. Okay, so I need to go to here. Okay, so what I want to do is go to this. I need to adjust something. So bear with me just for a second. Okay, so I'm wanting to change something on our home screen. So I've got to go back to this class right now, this Zoom session. And Okay, this is on a Zoom session, so we're open and it's running, so it's not ending. So we're cool. Okay, sorry about that. So what I want to do now is go back to this problem right here. And one question that could be asked is, let's give the information on the situation. So first of all, let's ask this question. And I'll give an interval in just a minute. But on what interval, is there an absolute max on this function? Is there an absolute min? That earlier question we were asking, what's the domain of this function? Let's do that. What's the domain of this? There's no limitation. So this thing goes on forever to the left and it goes on forever to the right. So the domain of this is infinity to infinity. It's all real numbers, okay? And where is it continuous? Everywhere, negative infinity to positive infinity. Now, you're asked, okay, what is the shape of this? What's the shape of the graph? It's a cubic function, and it's got some extra goobers in the middle, so that means it looks like something like that. So that means we've got situations where we're going to have a max, a local max, and a local min. All right? Have that going in your head. You know that's going to happen. So let's see what those are. So first we got to find the critical numbers. Find the critical numbers of this function. And we're going to say, where is this increasing and where is it decreasing? Notice where it's increasing. To the left of this critical number. Increasing to the right of this critical number. Where's it decreasing? In between the two critical numbers. Okay? So let's get the answer to this. Now, so we got to take the derivative. Where are the critical numbers first? So we're going to set this, take the derivative. We get 6x squared minus 18x plus 12. Right? Critical numbers. We got to set this equal to 0. Factor it and set it equal to 0. This equals 6 times x squared minus 3x plus 2. I hope you're comfortable with doing that on your own. Factor this now. I'm going to pause just for a second. Factor it yourself. See what it would be. And that's going to be, yes, it's going to be x and x. It's got to be 1 and 2. They're both the same sign because it's positive. Because the positive 2 is. And they both got to be negative because we get negative 3x in there. All right? So there is a factored form. Now what are the critical numbers? Set this equal to 0. So we've got 0 equals, I'm going to put 6. We don't need the 6. So I could divide each side by 6 right now and get this. This is an appropriate next step when you're doing the problem. Therefore, x minus 1 equals 0 and x minus 2 equals 0. Give us the critical numbers. X equals 1, x equals 2. So where is the function? So what's going on? So get a picture in your head. The graph looks like this. Therefore, this must be x equals 1. This must be x equals 2. We don't know the y value. You got to plug it into the function to figure that out. But we know if you're asked on what intervals is it increasing, it's increasing on intervals on, you can see that over here, it's negative infinity to 1. Union with, here also, right? 2 to infinity. All right? And decreasing on the interval, you see what it is? 1 to 2. Not including the endpoints. It's not increasing or decreasing at the endpoints, okay? Now, is there a local max anywhere? Yes, there's a local max right here. You can see that. Local min right here, all right? And notice, in a second, we're going to talk about the first derivative test. Would say, what we can do is figure out the first derivative to the left of 1. We can figure it out in that function. And then figure out, so the first derivative test, what you got to do is check if it's increasing or decreasing in between the critical numbers. So what I would do is I would pick a number to the left of 1 that's easy to work with. I'd pick 0 here. I'd pick what's in between. 1.5, that's not exactly fun. Real easy to work with, but that's 3/2. But again, all we're doing is we're going to just plug it in. Do we want to know if is it positive? Is the slope positive or negative here? Okay. So that goes there in between. I pick a number in between. And to the right, I'll pick the smallest number that fits. I'll pick 3. Okay. So if I plug those in, those three values into the first derivative, I'm actually doing the first derivative test. So the first derivative test says, first derivative test is, what's the slope like? Do I have a local max or a local min? You can tell by the graph what the answer is there. It's a local max at x equals 1 and a local min at x equals 2. But let's use the first derivative test to say it. Check it out. So if I figure out the slope at the 3 points that I picked, f of 0, f prime at 1/2, 1.5, and f prime at 3, I can plug in and figure out if the slope is increasing or decreasing, is it positive or negative there. So when I pick f prime at 0, I take the derivative now, which is, it's up here. This is it, the derivative of this. Plug in 0, I get 0 minus 0 plus 12. That equals 12. That's positive. So the answer is, first derivative test, I've got a positive value to the left. What is it in between? 1.5. You can plug 1.5 into the function from the beginning, but look what I can also plug it in here. I've broken it apart. So the function is equal to 6 times 1.5 minus 1 times 1.5 minus 2, right? All right, and I don't even have to get the answer necessarily, but I do need to recognize the sign. My goal of the first derivative test is to figure out what the sign is. So I could get the answer and multiply it out and get the answer, but all I'm going to worry about is the plus or minus. So let's get the answer. 1.5 minus 1 is positive, right? It's positive 0.5, but it's positive. And when I do this one here, I get 1.5 minus 2. Notice I get negative 0.5. So what is the answer? Is it going to be positive or negative? The number isn't critical because I just want to know if the slope's increasing or decreasing. I get 6 times 1/2 gives me 3. 3 times 1/2, negative 1.5. It's going to be 1.5. But the biggest thing is it's a plus times a plus times a plus times a minus. That answer is negative. So in between here is negative. And that confirms what we're saying the first derivative test tells us, okay? Now, look at the next one. Look at f of 3. So coming here at f of 1.5, it's going down. So at f of 3, what do we get? We get, plug that into any function you want to. Let's plug it into the factored form again, okay? And again, I'm just worried about the signs. So I get a plus, I get a plus, I get a plus. So in this situation, the answer is positive. So the situation here is we get a plus. So for the first derivative test, this says that we've got a positive, it's greater than 0 coming here, and then it's less than 0 to the right of 1. Therefore, we've got a local max at x equals 1. And here, it's negative to the left of 2, and it's positive to the right of 2. Therefore, we've got a local min at x equals 2. Okay? That is the first derivative test. That's using the first derivative test. So the idea is, again, if it's negative changing to positive, or if it's positive changing to negative, it verifies you got a local extrema. Negative to positive gives you a bottom, a min. Positive to negative gives you a upper, a top. That's a max, okay? So that's that situation. I tell you what, I think I want to stop there. And do you have any questions about that at all?